Your sky full of stars, 'cause you light up the path. I don't care, go on and tear me apart.
Okay, and welcome to this video on fluid flow. As you can see from this wonderful picture, the fluid flow has many uses, one of which is what we call aerodynamics and is used by Formula One racing cars, isn't it? They change the shape of their car because they want to move through the air in the most efficient way. And what they really want is these straight lines, that's the way the air is flowing, and they don't really want that to change much as it flows over the racing car. If those lines sort of become circles, that means the drag is increasing and there's an increase in resistance that's going to slow the car down. So when Formula One racing cars are being designed, or all cars really, you want to minimize the drag, and that's when you want to see these straight lines going over and not this curly stuff that you see at the end. That's going to cause resistance. Okay, let's dive right in. Here we're going to be talking about density, which equals to mass over volume. We're going to know upthrust equals weight of liquid displaced, and we're going to talk about something called Stokes' law, and then what we just mentioned, laminar flow and turbulent flow, the two ways in which we can describe the flow of fluid over an object. Let's dive in. Okay, some words we're going to look at: laminar flow, turbulent flow, fluid, which means liquid and gas, don't forget, upthrust, which we'll talk about in the next slide, viscous drag, that's going to be calculated by the Stokes force, viscosity, which is the thickness of a fluid, density, mass per unit volume. Okay, upthrust, what is it? An upward force exerted by a fluid on a submerged or floating object. Don't forget that when we talk about fluid, we're talking about liquid and gas. So when an object is placed in a field of a liquid, then it's going to move some of that liquid out the way. And the amount of liquid that it displaces or moves out the way, the weight of that displaced fluid is equal to the upthrust, and it provides an upwards force. Why does it provide an upwards force? Well, let's have a look. We don't really need to talk about those slides. We can see that when an object has a top part and a bottom part, and we know that when we move down in a liquid, the pressure increases. So it makes sense to say that the pressure on the bottom surface is going to be greater than the pressure on the top surface. So the force pushing upwards on the bottom surface is greater than the force pushing downwards. That difference provides a resultant force upwards, which is what we call the upthrust, and it's equal to the volume of the liquid displaced. Here we can just briefly explain why there is a difference there. We know that H1 is the height, the depth of the liquid, and we know that rho GH gives us the pressure, times the area of the surface gives us the force applied on that surface. Yeah. Here we've got H2 according to the depth that the object is at. The second surface is at a greater depth, so there's a difference in force there. Yeah. The net resultant force is going to be upwards. That is the upthrust. Well, that is why we have upthrust, and we can calculate the upthrust as the weight of the liquid displaced. How are we going to get the weight of the liquid? Well, we need to know the volume of the object. That will give us the volume of the liquid displaced, and then we just times that by the density of the liquid, and that will give us the mass of the liquid, and then we multiply again by gravity, which is 9.81 at AS level. Okay. Let's do a quick question. A steel sphere of diameter 2.7 centimeters is immersed in oil of density 900 kilograms m to the minus 3. Find the resultant force on the sphere at the moment that it is released. Density of steel equals 8,100 kilogram meters to the minus 3. Okay, so we just talked about it. We're going to want to calculate the volume of the sphere, and 4/3 pi r cubed is the volume of the sphere. Notice how the diameter here is given in centimeters, and it's also the diameter, so we're going to want to halve that to get the radius and put it into meters. That's a common mistake at this level, so always remember, if it's diameter, you're going to need the radius, right? Let's have a look. Volume of sphere, 4/3 pi r cubed, 4/3 times pi, and then we've converted that. Okay, so I was looking at that, then I was like, what? Oh yeah, so that's 0.27 is in meters divided by 2. Okay, and then we've got our answer, the volume of the sphere. Okay, great. Next thing we're going to want to do is calculate the mass, which we talked about just now is the density times the volume. The density of the fluid displaced is 900. Wait, what is it? Is that the density of the oil? Yeah, density of the oil, 900 kilogram meters to the minus 3 times by the volume, which we just calculate. That gives us the mass of the fluid displaced. And then if we want to know the weight of the fluid displaced, what we're going to need to do? Multiply by what? You tell me. You're correct. Multiply by g, gravity, which is 9.81. So now we have the force upwards, which is the upthrust, 0.088 newtons, and we want to calculate the weight. A weight is going to be the density of the object, which is steel, times by the volume, which we've calculated. Yep, density of volume, and then times by g to get the weight. So that will give us the mass, and then times by g to get the weight. Calculate it out, we get 0.795, and we know that weight is always down. So 0.7 is down. We can quickly see this is 0.08. So the weight is much bigger than the upthrust. So the object is going to move down with a force of 0.71 newtons. Pause the video, check the calculations. You can go back and forth and look at the question. Anyway, in the meantime, let's go on. Okay, and then here's some questions for you to do yourself. The first one is just calculating the volume, making sure you can do that by changing the various measurements, making sure you put them into meters and not centimeters or millimeters. Then it says find the mass. Well, that's going to be the density times the volume, and they've given us the densities, and you can calculate that. And then here is doing a question all on your own. I'm just going to have to quickly move myself out of the way. Okay, there we go. And here you can see that question is similar to the one we've just done. Okay, calculate the upthrust. Which way will it move? Okay, pause the video. Then I'll give you the answers. Okay, let's go on. Okay, answers are... Okay, here you go. Take a look at those answers. I think one of these is incorrect. I can't remember which one it is. I got it out of the textbook. It's one of these answers is incorrect, so just ignore it and find it yourself. I'll put it in the comments at the end. 3, same as what we was talking about, and I think part 3 also asks us to sketch the shape of fluid flow, which we haven't talked about, but I'll talk about it on the next slide. Okay, pause the video, check your answers. If any questions, leave them in the comments. Right, here's how we draw a diagram. Now, for our diagram in the last question, it's going to be similar to this, but it's going to be rotated 90 degrees because this object is moving from right to left. And we're talking about an object in the last question that's moving in a vertical direction. I think it was moving upwards, right? The last question, yeah, it's moving upwards, so it's going to be in the vertical plane. We're just going to rotate this diagram 90 degrees, and otherwise it should be the same, isn't it? Yeah, because this object is moving to the right. How do we know it's moving to the right? Because the liquid is flowing over it to the left, isn't it? Obviously, if you're pulling an object, the liquid's going to go in the other direction. This is the drag force, the viscous drag that is being caused by the object. We can see here on picture A that it's smaller than on picture 2, and here we've got turbulent flow coming off it. That's also adding to the viscous drag on the object, slowing it down. Okay, so we don't want to see any of this. And here there's just so much, the viscous drag is much bigger. So we've got much more turbulent flow. Here we've got just laminar flow, nice and smooth, minimizing the drag force on the object that's being moved through it. Okay, let's have a look at a question. Which force is caused only by a pressure difference? Pause the video, take 1 minute. And okay, let's give you the answer. Answer is, of course, B. Which force is caused by a pressure difference? Well, we just mentioned that it's upthrust. Friction, on the other hand, is caused by objects rubbing each other together. Viscous force is a fluid on the surface of an object. And weight is the mass times the gravity of the object acting downwards, so it's none of those. Stokes' law, this is the law that enables us to calculate the drag, the viscous drag force acting on an object as it moves through a fluid or as a fluid moves over it. Okay, so 6 times pi times eta times r times v. 6 times pi we know times eta, which is the viscosity, the thickness of the fluid, is going to be a value. Thicker the fluid, the higher the viscosity. R is the radius, because we're only talking about a sphere for Stokes' law to apply. And V is the velocity. So that's just one law, enables us to calculate the viscous drag. We can just remember it, 6 times pi times eta times r times v. If we go across the next slide, we can see conditions for Stokes' law to apply. Stokes' law. The object moving through the fluid must be relatively small. The object must be spherical. The object must be moving through the fluid with laminar flow. And the object must be moving slowly through the fluid. Okay, so slowly, small, laminar flow, and spherical for Stokes' law to apply. Okay, so let's have a look. When an object moves through a fluid or a fluid moves past an object, you get friction between the surface of the object and the fluid, fine. This friction is known as viscous drag, right? So that's our force there that we're talking about. It's acting in the opposite direction to the motion, so we can call it friction, a type of friction. You can calculate the force due to viscous drag on a spherical object moving through a fluid using Stokes' law. Viscous drag depends on the viscosity or thickness of a fluid. Viscosity itself is dependent on temperature. As the liquid, as the temperature increases, then the liquid itself gets less viscous. It's easier for the object to move through a hot liquid. But gases, on the other hand, are the opposite. They get more viscous as temperature increases. So we just have to remember it's the opposite for gases. Okay, let's move on. Have a go at this question. Just pause it and then I'll give you the answer. Okay, a table tennis ball of diameter 40 millimeters and mass 2.7 grams is dragged through the water of viscosity 0.001 Newton seconds meters to the -2 at a speed of 5 meters per second. Calculate the viscous drag and comment on your answer. Okay, so what do we need to notice here? We've got a tennis ball that's moving through a liquid. The diameter is 40 millimeters, but we're going to want to change that into meters. And we're also going to want to half that to give us the radius, aren't we? Yep. The mass is 2.7 grams. We're going to need to change that into kilograms. And the viscosity of the liquid. So we can just straight away just use Stokes' law here to calculate out the viscous drag, which is given by F equals 6 times pi times eta times r times v. We know 6 times pi, that's that. Times eta, which is the viscosity, it tells us there, times by r, which like we said, we need to half and put it into meters, 0.02, and multiplied by v, which is the speed that the object is moving through the liquid. That gives us 1.8 times 10 to the -3 newtons. Okay, what do we notice about that? This is a very small force, 1.8 times 10 to the -3, much less than the weight of the ball. Okay. What else does it say there? I'm just curious. Okay, suggesting that the conditions for Stokes' law do not apply. So is it saying that the force is too small even for Stokes' law to apply? Okay, next. Talking about laminar flow, we briefly mentioned it before. This is two types of flow. So when an object is moving relatively slowly through a liquid, and it's more streamlined, it's going to get this type of flow. So this object is obviously moving to the right because the flow of the liquid is going over it in that direction. The lines are almost what we call parallel. the direction is parallel anyway, and we want them to be as smooth and not like this, which is turbulent. Yeah, that's going to be laminar flow with the path of least resistance. This one, as the speed increases, this is what we call turbulent flow, and that is going to give us maximum resistance and increase in drag. Okay, we don't really need to have a look at this. You can pause it and read it if you want. It's the same thing as what we talked about. Okay, now we're going to talk about terminal velocity. When an object is at terminal velocity, what did I press? Okay, when an object is at terminal velocity, we're going to end up with something like this. These are the force. Okay, maybe this is this telling us it's forces on a sphere falling through a liquid at terminal velocity? So when these balance, up thrust plus viscous drag equals weight. So that's when the weight is equal, the forces are balanced. It must be at terminal velocity. Let's have a look at this question. It's going to explain what we're talking about here. An air bubble in a tank of water is rising with constant velocity. Key is it's rising, it's moving upwards with constant velocity. What does that mean? The forces are balanced. The forces acting on the bubble are x, y, and z as shown. So we just have to say which is x, which is y, which is z. Okay, we know that weight always acts downwards. We know that up thrust always acts up. So x is up thrust. Y or z is weight, and one is drag because it's moving. So there's viscous drag. Because it's an air bubble, we're going to say that the weight is very small. So we're going to say that y is weight, and z is going to be the drag on the bubble, which balances it out. So z is the viscous drag, y is the weight of the bubble, x is the up thrust. The answer is A. Just talked about that. That's going to give us terminal velocity. So to expand on this idea further, when the forces are balanced, the up thrust and the viscous drag equals the weight. The object is stationary or in terminal velocity. So when it's at terminal velocity, we know that the up thrust, which is equal to the weight of the fluid displaced, we can calculate the weight by the volume times the density times gravity, isn't it? So that's all this is. The volume times the density times the fluid, the density of the fluid times gravity, which is 9.81 plus the viscous drag, Stokes' law, 6 times pi times eta times r times v. That is the viscous drag, equals to the weight, which again is the volume times the density of the object, in this case it's steel, times by g. Okay, so we can narrow it down, and that gives us a formula for the terminal velocity, which as follows, and you can calculate that through yourself. Okay, have a go at these questions. Pause the video, and welcome back. Okay, here are the answers. The first question, gotta find a nice place to put myself. The first question is up thrust. So temperature. What happens? What is it? The question. Let's have a quick look. The effect of an increase in temperature will have on the terminal velocity. Well, it's going to fall faster, isn't it? Yeah. So the object will move, will reach terminal velocity later. This means it's going to have a higher terminal velocity. Here you can see that the second question is just using up thrust plus weight plus viscous drag is what we just talked about. You should be able to follow the answer there. Okay, and that's all really I wanted to talk about in this video. Please comment, subscribe, and let me know if you've got any questions. Thanks for listening.